It is one of the phenomenon exhibited by the light, wherein when a light ray passes from one optical medium to another optical medium, there is a change in the path of ray of light, which is known as refraction of light. In other words, refraction of light is the phenomenon of bending of a ray of light when it passes from one medium to another medium. Now let me consider some of the consequences of refraction of light. For example, twinkling of stars is also due to refraction of light. Another example is a coin placed in water appears to be raised when it is viewed from another medium. It is also due to refraction of light. Or else, if you consider one more example, when a stick is partially immersed in water taken in a jar, the stick appears to be bent. It is an example for refraction of light. Now let us consider optical medium is one in which the light passes. A medium through which light passes is called an optical medium. This is the interface separating two media, medium 1 and medium 2. This is the interface separating two media, medium 1 and medium 2. Now let me consider this is the rarer medium, this is the denser medium. A rarer medium is one in which refractive index is less. A denser medium is one which is having higher refractive index. Let us see what is the refractive index later on. Let us consider the perpendicular drawn to this surface is this. We call this as the normal. This is the normal. This is the interface separating two media. Now let me consider a ray of light is incident like this. This is the incident ray. A ray of light is incident at an angle of incidence I. Angle of incidence I is the angle between the incident ray and the normal. So in the absence of this second medium, the denser medium, the incident ray would have gone straight. But because of this second medium, which is the denser medium, the ray instead of undergoing going straight like this, it bends towards the normal. It has changed the path. This phenomenon of changing the path of ray of light or phenomenon of bending of a ray of light like this is known as refraction of light. So this is the refracted ray. I can write here. This is the refracted ray. This is the incident ray. This is the angle of incidence. So this is the angle of refraction. Angle of refraction is the angle between the normal and the refracted ray. Now, in the diagram, you can observe that the deviation produced. This is the deviation produced, and it is denoted by D. Deviation is the angle between the refracted ray and the incident ray produced as it passes from one optical medium to another optical medium. From this diagram, you have to point to 3. Number 1 is when a ray of light travels from rarer to a denser medium, the refracted ray bends towards the normal. And the second point is angle of incidence I is greater than the angle of refraction. And also you can follow from the diagram that the deviation produced is this one. B is equal to, this is totally I, therefore this is totally I, this is the deviation. By mathematics we can show that B is equal to I minus R. So I will repeat this once again. When a ray travels from one optical medium to another optical medium, it undergoes refraction, it bends towards the normal, and angle of incidence is greater than angle of refraction, and the deviation produced is D is equal to I minus R. On the other hand, this is the interface separating two media, and the normal to this surface is this. Okay. Now let me consider this is the medium 1, in which you can consider this to be a denser medium, and this is the medium 2, which is considered to be rarer medium. Let me consider a ray of light is traveling from denser to a rarer medium like this. This is the incident ray. So, angle of incidence is the angle between the incident ray and the normal. In the absence of this second medium, which is the rarer medium, the incident ray would have gone straight along this direction. But because of this second medium, of course it may be a rarer medium, it has undergone refraction. How it undergoes refraction? From the diagram we can see that it has bent away from the normal. That means when a ray of light travels from denser to a rarer medium, the refracted ray bends away from the normal. So this is the angle of refraction. I can take this as small r, and the deviation produced is denoted by d. This is the deviation produced. In this case, 3 points you have to remember again. When a ray travels from denser to a rarer medium, the refracted ray bends away from the normal. And the second point is this angle of refraction, that is r, is greater than the angle of incidence, that is I. And the third point is the deviation produced is given by r minus I, because r is greater than I. So, what you can observe from these two diagrams is, wherever there is an incident ray, that medium is considered to be 1. Wherever there is a refracted ray, that medium is considered to be 2. Similarly, here also, a ray of light is traveling from denser to a rarer medium. It is traveling from denser to rarer medium means denser medium is considered to be medium 1, whereas the rarer medium is considered to be medium 2. So, please see the difference between bending of a ray of light when it travels from rarer to denser medium or from denser to a rarer medium. Now, let us pass on to laws of refraction. There are 2 laws of refraction. First law is the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. This is the incident ray, this is the refracted ray, and the normal at the point of incidence all lie in the same plane. This is the first law of refraction. The incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. And second law is the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media and for a particular wavelength of light. Just I can write here the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media like 1 and 2, and for a given wavelength of light, for a particular color of light. This constant is called refractive index of medium 2 with respect to medium 1. This can also be written as N21, that will be equal to N2 divided by N1. This constant, I can repeat this once again, is known as refractive index of medium 2 with respect to medium 1, which can be written as N21 is equal to N2 divided by N1. This is called Snell's law of refraction. This is known as Snell's law of refraction. In the examination, we will ask you for 2 marks. State and explain Snell's law. Snell's law of refraction is the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media, that is most important, and for a given wavelength of light. This constant is called refractive index of medium 2 with respect to medium 1. That is equal to N21 is equal to N2 by N1, which is nothing but the Snell's law of refraction. This Snell's law has one of the limitations. Now let us see what is this limitation of Snell's law. For example, if the angle of incidence is 0, that means a ray of light is incident along the normal. A ray of light is incident along the normal. For normal incidence, I is equal to 0. The ray will not undergo refraction. There is no bending of ray of light. Therefore, angle of refraction is also 0. If the angle of incidence is 0, angle of refraction is also 0. Sin A by sin R becomes 0 by 0. We cannot define this. So, this is one of the limitations of Snell's law. That means Snell's law does not hold good for normal incidence, because for normal incidence, angle of incidence is 0 and angle of refraction is also 0. Absolute refractive index. Now let us see what is this. Absolute refractive index is denoted by N. It is defined as the ratio of the speed of light in free space to the speed of light in a given medium. That is given by N is equal to C by V. That means to say that the speed of light is the ultimate speed in nature, and as the light ray passes from the free space to another medium of certain refractive index, the speed will decrease. So, the speed of light in a given medium is V. If you take the ratio of speed of light in free space to the speed of light in the given medium, then it is denoted by N. We call this as absolute refractive index. Absolute refractive index is defined as the ratio of speed of light in free space to the speed of light in the given medium. As I told you, the speed of light in free space is the ultimate speed, is the greatest speed in nature. In any other medium, this speed is always lesser. Therefore, absolute refractive index N will be always greater than 1. This is because this value is 3 into 10 raised to 8 meter per second, and this value is less than 3 into 10 raised to 8 meter per second. Consequently, using mathematics, we can say that N will be greater than 1. So, absolute refractive index will be always greater than 1. Now, let us consider another term, that is relative refractive index. Relative refractive index is defined as refractive index of one of the medium with respect to some other medium other than air or vacuum. For example, a ray of light is traveling from first medium, that is air, glass, for example, to another medium, that is water. So we can write the diagram like this. Okay, glass to water. This is the glass medium. This is water medium. This is the denser medium. This is the rarer medium, of course. Now, the speed will change. Okay, that means refractive index of one medium with respect to some other medium, we can take like this, or refractive index of one of the medium like water with respect to some other medium like glass other than air or vacuum. That can be written as refractive index of glass with respect to water, or refractive index of water with respect to glass. So, NGW is defined as the relative refractive index, or NWG is defined as the relative refractive index. That means refractive index of one of the medium with respect to some other medium other than air or vacuum is known as relative refractive index. This is similar to the saying that refractive index of medium 2 with respect to medium 1, which is equal to N2 by N1. Like this can be written as refractive index of glass with respect to water, that is Ng by Nw. This can be written as refractive index of water with respect to glass Nw by Ng. Now, as I told you, this is the denser medium. That is, glass is denser, whereas water is rarer. Okay, denser medium is having higher refractive index, whereas the rarer medium is having lesser refractive index. If it is so, Ng by Nw, refractive index of glass is greater than refractive index of water, means this will be greater than 1. Nw by Ng by mathematics, refractive index of water is somewhat lesser than that of glass. If it is so, this will be less than 1. So, relative refractive index, it may be greater than 1 or it may be less than 1. Whereas, absolute refractive index will be always greater than 1. Some of the important points that we have to note here are why does refraction of light is. The refraction of light is due to the reason that when a ray of light travels from one medium to another medium, its speed changes. Due to change in the speed, there is a change in the path of ray of light. This is the first point you have to remember. And the second point you have to remember is, when a ray of light travels from one medium to another medium of different density or optical density, then one of the important physical quantity does not change is the frequency. The frequency does not change. Whereas the physical quantities like velocity and wavelength, they do change when a ray passes from one medium to another medium. So in the examination, we will ask you, name the physical quantity that does not change when a ray of light travels from one medium to another medium. The answer for this is the frequency. Name the physical quantities that change when a ray travels from one medium to another medium. They are the velocity and wavelength. Also nothing but refraction through a parallel sided glass slab. In other words, this is known as lateral shift that you can observe when a ray passes through a parallel sided glass slab. Now let me consider this is a parallel sided glass slab. This is a denser medium, wherein this is a rarer medium. Now let me consider this is air and this is glass. Here is a rarer medium, glass is the denser medium. Now let me consider this is the first interface. This is the interface separating two media like rarer and denser, and this is the second interface separating two media, that is glass, and then this is air. Of course, this is the rarer medium again. Now let me consider the normal to this surface. Normal to this surface is this. Okay. Let me consider a ray of light is incident from rarer to this glass medium, that is the denser medium, at certain angle of incidence. PQ is the incident ray. The angle of incidence is denoted by I. In the absence of this denser medium, that is the glass medium, the incident ray would have gone straight. In the absence of this denser medium, the incident ray, they have gone straight like this. The dotted line indicates the direction of the incident light. But because of this denser medium, it undergoes refraction. How it undergoes refraction? It bends towards the normal. And incident at the second interface, it has undergone refraction. The refracted ray bends towards the normal, and the angle of refraction is R, and the refracted ray is incident at the second interface. Suppose if I write the normal at the second interface also, this angle will be equal to this angle, alternating angle. Of course, you'll be knowing that. Again, the ray of light is traveling from denser to a rarer medium. It bends away from the normal. It bends away from the normal. And it is observed that this is the emergent ray. The emergent ray is RS, is parallel to the incident ray produced. That means there is a sideways shift for a ray of light incident on a parallel sided glass slab. This sideways shift is known as the lateral shift. So this can be measured by drawing a perpendicular line on the incident ray from this point. So RT gives the lateral shift. So the angle of emergence is I dash. I will repeat this once again. Let us consider a ray of light PQ is incident on the first interface at an angle of incidence I. Because of the second medium, that is the denser medium, which we have considered to be glass, it has undergone refraction. It bends towards the normal. In the absence of this, the incident ray PQ would have gone straight. But because of this glass medium, it has undergone refraction along the direction QR. And again, this undergoes refraction at the second interface. It bends away from the normal. So RS represents the angle of emergence, emergent ray. So the angle of emergence is denoted by I dash. It is found from the diagram that when a ray of light is traveling through a parallel sided glass slab, there is a sideways shift. This sideways shift, we call this as the lateral shift. That can be measured by drawing a perpendicular to the incident ray from the emergent ray. You have to remember two important points regarding this lateral shift. When a ray is passing through a parallel sided glass slab, angle of incidence will be equal to angle of emergence. And the second point is there is no deviation of the incident ray. That means incident ray after passing through the parallel sided glass slab, it emerges such that emergent ray is parallel to the incident ray. So the deviation produced is 0. In the examination, we will ask you to define lateral shift. When a ray of light is passed through a parallel sided glass slab, the emergent ray will be parallel to the incident ray produced, and hence we can say that there is a sideways shift for the incident ray. This is known as the lateral shift. How can we measure the lateral shift? By drawing a perpendicular line between the emergent ray and the incident ray. In the diagram, RT measures the lateral shift. The two important key points regarding this lateral shift is angle of incidence is equal to angle of emergence. And the second point is the deviation produced is 0. We can show that lateral shift is equal to T divided by cos R into sin of I minus R. Lateral shift can be shown using a derivation. Ls is equal to T by cos R into sin of I minus R. That means lateral shift depends on the thickness. It also depends on the angle of incidence corresponding to which angle of refraction is there. Also, it depends on the refractive index of the denser medium and also refractive index of the rarer medium. So lateral shift can be shown to be Ls is equal to T by cos r into sin I minus r. Lateral shift depends on the thickness of the glass slab and angle of incidence, refractive index of the denser medium, and also refractive index of the surrounding medium. Next, we shall pass on to another important concept, that is the normal shift. Now let us consider an object is in the denser medium. I can write the diagram. This is the rarer medium. This is the denser medium. Let me consider an object is in the denser medium. Let O represents the object which is kept in the denser medium. A ray of light coming from this object, incident normally, it passes undeviated. For normal incidence, there is no refraction of light. This is one of the limitations of Snell's law, as you know. A ray of light coming from this object, incident along the normal, passes undeviated. Let us consider another ray coming from this object, incident at the top surface obliquely, like this. It is incident obliquely at certain angle of incidence. But the angle of incidence is denoted by I. I is the angle of incidence. Let this point is, let this be P. In the absence of this medium, it would have gone straight. But because of this rarer medium, as the ray is traveling from denser to a rarer medium, it bends away from the normal. It bends away from the normal. That means this is the refracted ray. PQ is the refracted ray. If you back produce the refracted ray like this, if you back produce this refracted ray will meet this normal ray at this point. This is the position of the image. That means when the object is kept in the denser medium, when it is viewed from the rarer medium, the object appears to be raised along the normal. This is known as normal shift. So this distance is the real depth. This is the apparent depth. So refractive index of this medium is N. This is of course the absolute refractive index. Can be shown to be the ratio of real depth to the apparent depth. That is, N is equal to real depth divided by apparent depth. That is given by Ns is equal to P into 1 minus 1 by N. I'll repeat this once again. When the object is in the denser medium, when it is viewed from the rarer medium, the object appears to be raised along the normal. That is known as the normal shift. Let me consider an object O is in the denser medium, like this, of refractive index N. A ray of light coming from this object incident along the normal, it passes undeviated. For normal incidence, there is no refraction. Another ray coming from this object incident at certain angle of incidence, it undergoes refraction, so that is, it bends away from the normal. The ray is represented like this. If you back produce the refracted ray, that is PQ, it meets at a point I on this normal ray. This is the position of the image. That means when the object is viewed from the rarer medium, it appears to be raised along the normal. It appears to be shifted to the position I. Therefore, this gives the apparent depth, whereas this is the real depth, which is nothing but the thickness of this medium. Now, refractive index of this denser medium, which produces the normal shift, is given by n is equal to real depth divided by apparent depth. We can also show this normal shift ns is equal to t into 1 minus 1 over n. The simple examples for normal shift are: number 1 is a coin placed in water appears to be raised. That is, the real depth is greater than the apparent depth. And second one is the floor of the swimming pool appears to be nearer when viewed from the rarer medium. These are the two important examples for normal shift. Now let us pass on to another important concept, that is critical angle and total internal reflection of light. Critical angle and total internal reflection of light. Let me consider this is the interface separating two media. This is the rarer medium, whereas this is the denser medium. Okay, this is the denser medium, this is the rarer medium. Let me consider an object is kept in the denser medium. Object is O. A ray of light coming from this object, incident along the normal, it passes undeviated. As you know, in principle, a ray of light coming from this object, incident along the normal, passes undeviated. Another ray coming from this object, incident at certain angle of incidence, it undergoes refraction. Since it is traveling from the denser medium to a rarer medium, it bends away from the normal. You are all aware of this. As the ray is traveling from denser to a rarer medium, it bends away from the normal, such that angle of refraction is greater than the angle of incidence. As the angle of incidence increases, angle of refraction also increases. The meaning of this is, if you further continue writing another incident ray, angle of incidence increases. Correspondingly, angle of refraction also increases. If it is so, if you consider one more ray coming from this object, incident at the interface, like this, this is the normal. For this particular angle of incidence, that is known as the critical angle, the ray grazes the interface. In this case, angle of refraction becomes 90 degree. That means C is the critical angle. Critical angle for a pair of media is that angle of incidence in the denser medium, for which angle of refraction becomes 90 degree. I'll repeat this. Critical angle for a pair of media is that angle of incidence in the denser medium, for which angle of refraction is 90 degree. For example, if you consider another ray of light coming from this object, incident at an angle greater than the critical angle. If you further increase the angle of incidence, that is the meaning. If it is going beyond the critical angle, the ray, instead of undergoing refraction, it rebounds, it reflects back into the same medium, like this. This phenomenon is known as total internal reflection of light. Total internal reflection is one of the phenomena of light in which, when a ray of light is traveling from denser to a rarer medium, if the angle of incidence is greater than the critical angle, the ray, instead of undergoing refraction, it reflects back into the same medium. This phenomenon is known as total internal reflection of light. The two sentences are very, very important. Critical angle is that angle of incidence in the denser medium, for which angle of refraction becomes 90 degree. And total internal reflection of light is one of the phenomenon in which, if the angle of incidence in the denser medium is greater than the critical angle, the ray, instead of undergoing refraction, it reflects back into the same medium. This is known as total internal reflection of light. In general, it is TIR, total internal reflection of light. There are two conditions for TIR of light. Number one is, angle of incidence must be greater than the critical angle, and second one is, the ray must travel from denser to a rarer medium. The two conditions for TIR of light are, angle of incidence must be greater than the critical angle, the ray of light is traveling from denser to a rarer medium. That's all about critical angle and total internal reflection of light. Now let us pass on to a small derivation, that is the relation between refractive index and critical angle. Relation between refractive index of a medium and critical angle. For this, let us consider a simple diagram. This is the rarer medium, this is the denser medium, this is the interface separating two media. Let me consider the normal to the surface like this. This is the normal, the surface. Let me consider a ray of light is incident at the interface with an angle of incidence that will be equal to C. If the angle of incidence is equal to critical angle, the refracted ray grazes the interface. So the angle of refraction becomes 90 degree. R is equal to 90 degree. Using this diagram, we can arrive at the relation between refractive index of the medium and the critical angle. Now, this is the incident ray. I can call this as medium 1 this is the refracted ray which is in medium 2, in the rarer medium, of course. This medium is having a refractive index N1 and this medium is having a refractive index N2. For example, if it is a denser medium, this is the rarer medium, for example, this is A, then N2 is equal to 1, which is for A. No need to consider this to be N1. Instead of that, I can take this as N. So, refractive index of air is 1, that will be equal to N2. Refractive index of the denser medium, I can take this as N1, it is represented as N. Now, we have Snell's law of refraction. Snell's law of refraction is N1 into sin I is equal to N2 into sin R. This has been obtained by N2 by N1 is equal to sin I by sin R. So, N1 into sin I is equal to N2 into sin R. After cross multiplication, you will get this. So, what is this N1 here? N1 is N into sin angle of incidence, that will be equal to critical angle N into sin C is equal to N2, that is equal to 1 into sin 90 degree. Sin 90 degree is 1, therefore N into sin C is equal to 1. This can also be written as N is equal to 1 by sin C. This is the relation between refractive index of a medium and the critical angle for a plane of medium. That is N is equal to 1 by